Welcome to QuaranTIME. In today's episode, we're going to be learning about germs and fractions. We're super excited to have you here. Hello to Mary from... Oh,
you keep scrolling.
It went so fast I couldn't read the state before it disappeared. Hello to Ember, to Maisie, to Hannah, to Claire, to King Potato, to Courtney, Adrian. We're super happy to have you here. Thank you for watching. And today we're going to start with an art showcase, real quick art showcase, because there were not quite as many entries for our Punnett Square art prompt as there have been for other ones. Then we'll have a science lesson on germs, our fact or fiction trivia moment, our math lesson on fractions, a riddle, and a fun engineering challenge. So that is our outline for where we're going today. And now, without further ado, I will share my screen with you to show you some of the fantastic Punnett Square art that came in yesterday. And whoops, I'm at the bottom of my slideshow. We got to start at the top.
All right.
Here we go.
So I'm going to say we are going to do a day where we talk a lot more about Punnett Squares.
Yes.
But I appreciate those kids who were, excited enough to do this. Yeah, like 3D. Like that's cool. A rainbow owl.
Love it.
Did you know that owls could be rainbow? It's just a recessive trait.
That's fantastic. We've got elephant ears on the rabbit and a dihybrid cross with flowers. So we've got tulips and roses, the different type, shape, and color of flower. Very nice. Wacky hair and wacky eyes. Nicely done, Matthew.
Some colors.
Yeah, beautiful flower colors. And we've got a 4-legged or a 2-legged dragon.
Ooh,
I like it.
That.
So the recessive one looks kind of like a T-Rex dragon.
Oh, here we have a genotype. Yeah.
Mysterious orange eggplant.
Nice job, Declan.
And I love Sanjana's art here. We've got dominant is a fit girl and recessive is an obese boy. So you only end up with 1 obese boy with this dihybrid cross, 3 obese girls, and then a lot of very athletic kids for the majority for the rest.
Oh.
And then we've got a monster with spikes or tail or no tail. Great job, Graham. Supersonic Punnett Square. Very nice.
Rory.
I love it. And a wonderful cat drawing here. Great job, you guys.
Colors.
Bunny rabbit with different colors.
The bow ties versus straight ties. So
nice.
It looks like the straight tie is the dominant and a bow tie is recessive.
I love it. I love it. And then we've got a winged monster.
1 eye versus 3 eyes. Oh.
And 1 eye versus 3 eye alien. And we've got spots versus stripes with these mushrooms here.
Colors.
A snowman style. Very nice, Haley. And a great dihybrid cross here with toasted perfectly marshmallows versus not toasted perfectly. And then bow ties.
Versus no bow tie. Yep.
Very nice. And good alligator. And then here's our DNA model. So we got a couple people did the origami version. Nicely
I thought we were
done.
saving DNA to the end.
Oh, we're saving DNA till the end.
But,
all right.
But I'm impressed with what you guys came up with.
You did. Your DNA models were fantastic.
Indeed.
Now, to start off our lesson on germs, I'm super excited about this one because I think that the microscopic world around us is just fascinating. We're going to start by looking at something that you have probably used before if you have ever made bread. This is baker's yeast, and when you buy it in the store, it's dehydrated. All the water has been taken out, and it looks just like sand. I will pour it into this container here, in fact, and show you kind of a close-up view. And if you've never seen yeast before in person, you'll see that sand is a pretty good description, except this sand is sort of rod-shaped. I don't know how well you can see with my webcam here, but it's kind of rod-shaped and uniform in size, and it has a distinctive smell. It's not, you can't smell it very well when it's dry, but we're going to pour it into this funnel here so it goes down into this bottle, and you guys can see that it's fairly sandy and clear.
Is yeast alive?
It is alive. And that's the cool thing about yeast. We're going to wake it up. So when you put yeast into bread dough, what happens is that this is actually a fungus. These are millions of microscopic little cells, and they're kind of clumped together in these pellets that have been dried. And then when you add water and food, these animals wake up. They are little miniature animals. So we've got one bottle that has a packet of yeast and sugar. And I have another bottle here that has flour. 1/4 cup of flour, and we're going to put yeast in this one too. Math Dad, can you hold this for me? And then I'm going to have Math Dad hold the tray. We're going to add water and put balloons over the top and see what happens. This is going to take a few minutes, so we're going to get it all set up, and then we'll introduce some other germs, and then we'll come back and check it. So here's our second packet of yeast, pouring it into our bottle. Now, people have been using yeast for centuries to make bread, centuries and centuries, but they have not been using it like this. 200 years ago, there was not a store you could go to where you could buy a packet of dehydrated yeast. So my question for Math Dad, and I know he'll be looking to the chat to see if you guys can help him, is how did people get yeast before if they didn't have stores and there was no dehydrated yeast that you could get at a store?
Amazon.
There was no Amazon.
Oh.
There was no Amazon. How did people get yeast?
Is this like San Francisco, like where they make sourdough bread and they would just kind of keep a start going?
Yes. So this yeast right here is very common, and you can find it pretty much anywhere. There's probably some on your skin right now, but it's not going to grow unless it gets in the right conditions, and we can give it those right conditions right here. So back in the day, people would have, I gotta make sure my water's not too hot. It's not perfect. So we're gonna pour water into this one, and then we're gonna pour water into this one, and then Math Dad, if you can put balloons over the top. So before refrigeration and before the creation of stores and online shopping, when people wanted to make bread, they would have what was called a start. And the start, I'm going to shake this one up a bit to make sure it's well mixed. The start would be yeast that was with flour and water. All right, there we go. The start would be yeast that was mixed with flour and water, and it would be alive, and you would need to feed it every couple of days by adding more flour and more water and mixing it around. And if your start died, you would need to go and get a start from someone else, or you would need to grow your own. And when you grow your own, you are making sourdough bread. Sourdough is wild yeast strains that you gather together, and then they tend to be a little bit slower than this yeast. This yeast is very robust, the baker's yeast that we use. It's one of the hardiest and the strongest strains of yeast, and it tends to grow a lot faster than the sourdough and wild yeast that you might cultivate if you're making sourdough bread. But you can make your own sourdough bread just by putting water and flour together and then making sure you feed it and refresh it, and you'll gather the wild strains of yeast that are wherever you live and make your own sourdough.
Wait, what are you feeding it and refreshing it with?
Flour, water. You can also use sugars if you want, but the flour and the water, to make sure that you change that out so that it has new food to eat, is really what you do. So it's kind of like having a pet. You got to feed your pet, right? Like if you have a dog or a lizard, you're not going to just go a week without feeding them. And your yeast is the same way. You can't not feed your yeast. You have to give it new food every few days. Now I'm going to bring these a little closer so you guys can see them. And because this water was so warm, this balloon has actually caved in a little bit because the bottle's cooling down a little now, but both balloons should inflate. This one is with sugar, and this one is just with flour, and we'll come back and compare them in a few minutes. But first, let's talk a little bit about the history of germs, because several hundred years ago, people thought that bad smelling air is what made you sick. And they said, if you go somewhere where the air is stinky, like a swampy area, then you're going to get sick. And Louis Pasteur was a scientist who said, I don't think that's quite right, because sometimes you'll have food that will go bad when it's in a perfectly nice, not bad smelly air area, and other times food would last longer. And he was trying to figure out exactly what was happening, and he designed a cool experiment where he boiled broth where there was a flask that curved, and in the flask that curved, the broth stayed broth. It didn't get all moldy and scummy. But in the flask where he broke that curve of the glass, the broth spoiled. There were tons of bacteria and fungi that came into the broth. And that was really the beginning of germ theory. The idea that sicknesses and when food spoils, that's caused by tiny little microorganisms, that dates back to Louis Pasteur. And when we talk about germs, we're usually talking about one of 4 different things. We're talking about bacteria, fungus, viruses, or parasites. And so I have some little germs to introduce to you in cartoon form. And we're going to start with our bacteria. So the first bacteria that I want to introduce to you is a good bacteria. This is a little cartoon version of lactobacillus. And I also had success with my yogurt making. And I wanted to show you that. So this little jar was full of just milk yesterday. But then I added a little tiny bit of yogurt to it. And I kept it at a nice warm temperature for about 8 hours. And now the milk is yogurt. And it's yogurt all because of this little guy, lactobacillus. You have lactobacillus inside you right now. And this is what we call a probiotic, because if you do not have this bacteria inside you, then that's bad. Lactobacillus helps you digest your food, and it helps protect you from other infections. And so this is definitely a good bacteria, a bacteria we like to have around. This one, on the other hand, is not a good guy. This is Salmonella. Salmonella has lots of little flagella. That's what these little dangly things are called that help it swim around and move around. And if you get Salmonella inside you, you get really sick with throwing up and having diarrhea. And it's often called food poisoning because Salmonella can be in food, and it's not good at all.
Oh, so a question came in asking, actually, it disappeared all of a sudden, but is yeast vegetarian? So can you eat yeast?
Is yeast vegetarian? That is a great question. So if you are a vegetarian or a vegan and you don't want to eat any other animals, then you kind of have to decide if yeast is an animal or not. It is technically an animal in that it gets its energy from eating other food. Animals get their energy from eating food. Plants get their energy from the sunlight. And nutritional yeast, which a lot of vegans use as a dietary supplement because it has the vitamin B12, that is also a strain of yeast that's just been dehydrated and dried out. Technically, it's a tiny little animal, but it functions a lot more like a plant. And I would argue that it's probably not sentient in the same way.
I thought it was a fungus.
It is a fungus, but a fungus is...
Fungus counted animals?
Fungi, you can argue that they are more similar to animals than they are to plants. Technically, we don't call them animals. I mean, they're fungi. They're kind of their own category, and yeast is in that category. So in my opinion, you are still a vegan and a vegetarian if you eat yeast. That's Science Mom's opinion, but you could debate it.
Does anything besides water wake up the yeast?
Does anything besides water wake up the yeast? The yeast will definitely wake up if it gets wet. I don't know of any other liquid that can wake it up besides water. It has to be hydrated because right now in the dormant state, that yeast cell is all dried out and it needs to be rehydrated in order to wake up. It's formed a little spore, like a little protective cover around it to keep itself alive, but it's like a seed. It's dormant and asleep, and then when it gets wet, it will wake up. And if there's food, sugar and flour and other things that it can digest, then it will start to replicate and you'll get more yeast. Good questions. Now, quick introduction to bacteria. In each of these examples, we're going to see a good guy and a bad guy. Now let's go on to viruses. So the first virus that we'll talk about is a good little virus. This is bacteriophage. It's a virus that infects bacteria. And in certain conditions, if you have bacteria that you don't want to have around, this little virus can actually do you a big favor by coming, attaching onto the bacteria, putting its little RNA into the bacteria, and kind of taking them over, and it wipes out the bacteria. But most of the time when we're talking about viruses, they are not beneficial, and we do not like viruses. This is rabies. Rabies is one of the most deadly viruses that we know of, and you can see it's got like the little kind of crazy eyes, mad eyes in this little cartoon version. And rabies is a virus that attacks our nervous system. But each virus is different with how it behaves. And I want to tell you a quick, interesting story about chickenpox. So most of you who are watching in the chat have probably had the chickenpox vaccine. But when I was a kid, I did not have the chickenpox vaccine because there was no vaccine. And it was just expected that at some point you would get chickenpox. It was a very common virus. And I remember I was sitting by my front window waiting to go to school and I would just finish breakfast. And I remember my mom coming over and saying, "What is that on your neck?" And I went, "What?" And there was a little spot on my neck. And then she looked some more, and sure enough, there were a bunch more spots. And she said, "Oh, you have chickenpox. You're not going to school today." And I was like, wow, this is kind of cool because I feel great. I just have some spots and I get to stay home. But then I got more spots and then I felt kind of blah, and it ended up being a little bit of a boring week for me while I was home all week and having chickenpox. But it wasn't much of a pain, and I thought to myself, this is really not a bad virus. But the virus came back. Almost 20 years later, no, it's almost 15 years later, when I had cancer, my immune system was repressed because of the medicine that I was taking to treat the cancer. And that virus, even though I had not had a single chickenpox for 15 years, that virus was still inside me, in my skin, lying dormant. And when it realized somehow that my immune system was not around, it erupted into a rash called shingles. And when I first felt the shingles rash, it was the most rough, bizarre rash kind of on the side of my torso. And I went to my dad, who's a doctor, and I said, what in the world is this? You know, a few hours ago I had nothing. Now I've got this rash. And he said, it's shingles. Come with me to the pharmacy right now because there's an antiviral that if we start within the first 24 hours, will really reduce it. Otherwise, you know, it's going to take over a huge area and be really painful. But it's fascinating to me that somehow this virus, and if you've had chickenpox as a young person, you do have the chance of it coming back as shingles later. Somehow it lies dormant inside your body, just waiting for the right signals to erupt into shingles. But when it erupts into shingles, it usually is just on one half of your body and on one section. So you can get it on your torso, you can get it on your legs, you can get it anywhere, but it's going to stay kind of in one area, which is really kind of strange and bizarre. Viruses are fascinating. We'll take just a couple more questions about viruses, and then we're going to talk about parasites.
So what happens when you add good germs and bad germs together?
What happens when you add good germs and bad germs together? It depends on where they're added, but it can be a battleground to see who is the stronger germ. So for example, let's take milk and lactobacillus again. If you add a little bit of lactobacillus to yogurt, and you're making yogurt in your kitchen, then there are going to be other yeast and bacteria around because they're everywhere and they're microscopic. But if you put this temperature of the yogurt up to about 100 degrees or so like a nice warm bath temperature, where lactobacillus really likes it, lactobacillus is like a superhero and it's going to just take over the milk and make sure that no other bacteria can get a foothold. But if you put some lactobacillus in here and then you keep the yogurt really cold, other bacteria are going to gain some ground and lactobacillus is not going to win that battle. So it all depends on the conditions. Certain bacteria do better in one condition than another. And this is why probiotics and friends like lactobacillus are so important, because if we have these guys inside our digestive tract, they keep other bacteria and other yeast, other fungal infections, they keep those guys from getting in. They protect us.
So are there foods other than bread that eat yeast?
Yes, so the brewer's yeast that we have our experiment going with right here is also used to make beer. And there are different types of fungus that are used to make cheese. So if you like provolone cheese way better than Swiss cheese or mozzarella better than other cheese, a lot of that has to do with the particular type of yeast or fungus strain that is used in making that cheese. Cheese is also a food where we have microorganisms that we kind of enlist to help us make it. Good question. And then let's mention really quickly too. So we talked about the rabies virus and this little bacteriophage as two of our examples, but there's another virus that's really in the news right now, and that's the coronavirus. And then influenza, we're just getting to the end of flu season. Influenza is a virus too, and we'll talk more about those in just a minute. But first, let's introduce some parasites. So I did a bit of looking, trying to see if I could come up with a good guy for the parasites, and I really couldn't. Because when you think about it, and parasite is our word of the day, a parasite is something that takes resources from another animal or another plant, and it doesn't give anything back. It doesn't give anything back in return. So if Math Dad and I have a partnership, and he makes the QuaranTIME worksheet for me, and then I do all the research, and then we put on this show together, then we're each contributing, we're each giving something. But if you have a situation where something is just a drain on your body, just taking things and not giving anything in return, that thing is a parasite. And I could not find any examples of these little single-celled microorganisms that were beneficial, except for one rather fantastic superstar called the mitochondria. Now, the first time I heard this, I could not believe it, and it blew my mind. Inside your cells, every single one of your cells, you have a tiny little organelle. That's what we call a little tiny membrane thing inside your cells called the mitochondria. And I'm going to use this little red blood cell guy to represent the mitochondria. The mitochondria is small, and it is the energy factory of your cell. It makes ATP, which is what your cell needs to have energy, just all the time. You would not be alive without mitochondria. And there is a lot of evidence telling us that mitochondria used to be its own little free bacteria self until a bigger cell came along, ate it, and then instead of digesting it and taking it apart, said, huh, this thing's pretty useful, let's keep it around. So mitochondria used to be its own little free living self all by itself, and then we took it into our bodies. And pretty much every living thing that we know of, almost most living things that we know of, most animals have mitochondria in them.
So it would have been a parasite, but it turned into something good.
Yes, it turned into a symbiotic relationship where we give the mitochondria a little home, they give us energy and work as like a little factory that provides power for our cells. So that's an example, millions of years ago of a little parasite gone right and helpful. But most of the time when we're talking about cells that are more complex and bigger, the protists, we're talking about bad guys like malaria and Giardia. So Giardia is a fairly complex cell. It's bigger. It's not as simple as a bacteria, but it is just one little guy. And this will make you very sick if you get Giardia, with diarrhea and other unpleasant things. And then malaria is an interesting organism because it has a life cycle that goes between mosquitoes and people. So it lives part of its life in a mosquito, and then it changes, kind of like an insect when it goes through metamorphosis, becomes different than it was as a larva. It changes when it gets into a human and acts a little differently. And malaria is a super dangerous illness.
So what's the difference between a virus and bacteria?
The difference between a virus and a bacteria, that's a great question, is that we can argue about whether viruses are really alive. If I take a bacteria, pretty much any bacteria, let's say E. coli, for example. If I take this little E. coli and I decide, or no, salmonella, sorry, this is salmonella, this is E. coli, but either one of them, if I take them and put them into a petri dish and give them the right conditions, give them food and water, they'll stay alive. And they can move around and respond to things that happen in that petri dish. But if I take a virus, like this little bacteria phage, or like COVID-19, and I isolate it, it's not going to live. It's not going to do anything differently because it can't reproduce without a host. It can't reproduce on its own. This bacteria can reproduce on its own as long as it has food and water, but the virus cannot.
Does the virus have DNA?
Viruses have DNA and RNA, but they don't have a cell. Viruses are not made of cells. It's DNA or RNA inside a little envelope of proteins, a little membrane with some proteins on the outside. And it works by tricking another cell to reproduce. So if the virus does not have a cell that it can attack, you will never have it reproduce. You will never get more viruses. It has to have a host. Now, I want to show you the midway point for our balloons real quick. And then the last thing I want to tell you about is a rather amazing case that they had with the flu several years ago. So here is the sugar one, and you can see that our amount of yeast and bubbles has gone way up, and the balloon is starting to inflate. And here is our one with the flour going much slower, but both of them are making some nice little bubbly sounds that I can hear, and both of them are producing gas, and that's what is inflating this balloon. And if you let these sit and wait for about a half hour, the balloon will get rather large. Although we're using water balloons, which take a lot more force to blow up than regular balloons, so we might not see our balloons get quite as large as they typically do. Did you have another question?
Yeah. Why is COVID-19 called COVID-19?
COVID-19 is called COVID-19 because the COVID stands for coronavirus, and there are other coronaviruses that we've seen before, like SARS and MERS. And then 19 stands for the year that it was first described. It was first described in 2019, so that's why you have the 19 at the end of COVID-19. Good question.
There's a question on what is sickle cell?
A sickle cell is a cell that does not have the right shape and is kind of like flattened at one end. That's a little bit of a tangent, and I want to make sure I have time to get one more thing in. So let's talk about how germs spread. This is the last little part of my lesson, is how germs spread. So with Louis Pasteur that we mentioned before, how he discovered like, aha, there is some small microscopic thing that is causing this broth to spoil. For a long time, they thought, well, germs just spread through fluids. Like if I'm sick and then I share food with someone else and my saliva touches their saliva, then that's how people get sick. But sometimes you can have diseases that can be airborne as well. And to illustrate this, I want to tell you about a famous case that happened in 1979. There was a plane with 54 people on it. And there was a problem with the engine, and so they were just on the runway for 3 hours. And during that 3 hours, the ventilation system on the plane that usually circulates the air through some filters, it was turned off. So people were breathing more of the same air that they would have if the ventilation system had been on. And there was one person on that plane of 54 people who had the flu. They had just barely gotten sick and they were starting to cough. Well, within 3 days, 72% of the people on the plane got sick with the flu. And this case was kind of a landmark case showing that the flu is transmitted through the air. It was published in the American Journal of Epidemiology. I said that totally wrong. Epidemiology. There we go. And it was a surprise just with how effective it was, that you could have these 54 people together for 3 hours, and they're not really even talking to each other. They're sort of separated throughout the plane, but you had most of them come down sick within 3 days. Now, in terms of the virus that we're dealing with right now, COVID-19, how could you get COVID-19? Well, the way to get a virus the easiest is if you get contact on your hands and then you touch your nose or your mouth. Because if you put your fingers into your mouth or your nose, that's kind of like giving the virus direct access into your body. So that's why you're hearing people say, don't touch your face, wash your hands more often. Those two things really do a lot to help you avoid getting sick. And one of the best ways that I can illustrate just how easy it can be to have this happen is by using some paint. I have a special lotion called Glo Germ that's really cool, because with Glo Germ, you don't see it until you get UV light on it, but a little bit of paint is going to work the same way. So let's pretend, just for fun, and this is the last little activity in our science lesson, let's pretend like me, science mom, I'm sick, and I cough in my hands. Now, normally we can't see germs, but if we could, they'd look something like this. I would have just put millions of virus particles all over my hands. And now let's pretend like I'm getting ready to clean up, and I ask Math Dad for some help, and I say, here, would you take this bottle and go put it down, and then take this one and put it down, and he's going to put those over on the floor there. And now let's take a look at Math Dad's hands. Now, Math Dad did not touch me. He just touched the bottles that I had touched. But if he doesn't wash his hands now, what's going to happen if he gets an itch on his nose? If he gets an itch on his nose and rubs his nose, or if he gets something stuck in his teeth and he's like, oh, I've got something stuck in my teeth, he could get the virus inside him too. And this is why it's so important to wash your hands, because viruses are so small we can't see them. And I did see last week a really good question about the color of DNA or the color of viruses. Viruses actually have no color because they're smaller than a wavelength of light. So they don't have any color that we can see.
Whoa.
Crazy, right?
Yeah.
They don't have any color that we can see, but they are abundant, they are everywhere, and the best thing you can do is to wash your hands. And then last but not least, I want to remind you that microbes are not just bad guys. You do have a lot of good guys working for you as well, like lactobacillus, and they do a great job of helping keep your body sick. And then you also have little warriors inside of you called your white blood cells, and they do a great job of recognizing germs and fighting infections as well. All right, that was our quick science lesson, and now it's time for fact or fiction.
All right, I looked these ones up today.
Yes, this is one of the first times that Math Dad has done all the fact checking, so he's going to try and quiz me this time, and you guys can help me out in the chat.
All right, Science Mom. Fact or fiction? There are more bacteria in your mouth than there are cells in your entire body.
Ooh, there are more bacteria in your mouth than there are cells in your entire body. So I heard this one in my college biology class, and I will say that the cells in my mouth, if we kind of blew them up so that my cells are this big, then a bacteria cell is only going to be like this big. Bacteria cells are way smaller than our cells. So I'm going to say true because my biology teacher in college told me this.
Well, your biology teacher is wrong.
Oh, no.
So I think back in the 70s, or at some point a few decades ago, they did a study, and there actually was this estimate that the number of bacteria inside your body was about 10 times more than the actual number of cells that you have. But more recent studies have showed that it's actually maybe 1.3 bacteria per one cell. So it's the numbers are close, and that's for your entire body. And
so
a lot of bacteria are more in your gut.
In your digestive system. So you do have more bacteria cells than your cells inside you, but not by a lot.
Right. And it's going to vary from person to person, maybe twice as much or half as much as the average. But yep.
Pretty cool.
All right. Fact or fiction? The most common blood type is B positive.
Ooh, that's an interesting one. Most common blood type is B positive. Of the people that I know personally, the most common blood type is B positive. The people, like the family members and the people I know well enough to know their blood type, that's what I'm seeing the most. But the question is that sample representative of everybody? I don't know. I'm going to say true.
All right.
False. Oh, I should have looked at the chat. I'm seeing several people in the chat say false.
It's false. So the actual most common blood type is O positive. Although,
really?
Yeah, but it's going to vary across different ethnic groups and races, but yeah, O positive happens to be the most common, and the positive blood type is typically more common than a negative. So we'll try to talk about blood types another time. All right, fact or fiction? Humans and mice share about 90% of genetic material.
Fact. That's true.
What?
Yes. So most of our genetic material is actually non-coding DNA that we're not entirely sure why we have so much of it. But then like the amount of cells or the amount of DNA that just kind of make you a mammal, you're going to share with every other mammal. And then the amount that like differentiates you from a mouse is going to be smaller. Yeah,
that's exactly right. So as high as 92% would match up with a mouse. Okay. All right. You got lucky on that one. All right. Fact or fiction? A human cell has over 50 meters of DNA.
50 meters? Okay, a human cell has a lot of DNA. And you're talking if you stretched it out end to end.
Mm-hmm.
It's not as long as 50 meters. I can't remember exactly how long it is. I want to say it's like 10 feet long or something.
I know the chat says true.
Uh-oh. No, I'm seeing some false in there.
Okay, it's false. Yeah, it's about 2 meters.
2 meters.
Yeah, about as tall as you are.
That's amazing. So take one cell, stretch out the DNA, it'll be as tall as you. And I will say real fast, yesterday's lesson on genetics, we did try and cover way too much than we had time for. And I asked my patrons, should we do a week of genetics? I'm having them pick what we cover next week. So next week will either be geology, ecology, and psychology, or it'll be genetics. And then whichever one we don't do next week, we'll do the following week. Awesome. All right. It's time for Math Dad.
All right, we're going to talk about fractions. So this will not be the most exciting math lesson you've ever had, but we keep coming back to fractions because they are important. And if you don't have a good foundation in fractions, you're going to struggle in a lot of different areas. So, okay. Fractions. Just a reminder of how they worked. So I'm just going to draw me some pizzas here and cut them into 4 pieces because they're like big slices of yummy, delicious pizza. All right, and then we could shade in all the actual slices that are there, and then anything that wasn't shaded, those ones had already gotten eaten. All right, so we're seeing some fractions here, and because I've sliced the pizzas into 4 equal pieces, then our fractions are going to be fourths. And we could actually count out these fractions. So here I see 1, 2, 3, 4 fourths. Here I see 1, 2, 3, 4 fourths. And down here, just 1 fourth. So we can add those together. So 4 over 4, so 4 fourths plus 4 fourths plus 1 fourth. And what does that equal? Well, with adding fractions, as long as we have the same denominator, then we're good to go. We can add all together. that is 4 plus 4 plus 1 for a grand total of 9/4, which is the same thing we would have gotten if we had counted 1, 2, 3, 4, 5, 6, 7, 8, 9/4. All right, so 9/4 is something that we call an improper fraction. And we say it's an improper fraction because the numerator is bigger than the denominator. But in truth, there's nothing improprietous about it. It's
a perfectly okay number.
It's a great number. And you know what? Sometimes writing it as an improper fraction is going to be what we want to do. It can make some calculations much easier. In particular, when we start talking about multiplying and dividing fractions, it's easier to write it as an improper fraction in most instances than it is to write it as a mixed number. But okay, how else could we write that 9/4? Well, I think we'd already, if we just looked at the pizzas, we would have said there were 2 full pizzas plus 1/4 of another pizza. So that would be 2 and 1/4. So this guy here is a mixed number. And the other one we said was an improper fraction. And it's super important that we understand both of those. They carry the exact same information. However, sometimes one form is going to be more useful than the other. And I'll tell you for sure, most people are going to have a little bit better intuition when they think about 2 and 1/4 rather than 9/4. And I mean, when the numbers start getting bigger, like 900/4, then we don't have a lot of intuition for how big that is. Whereas if we had written it as a mixed number, we'd probably have a better sense for it. So how does one convert back and forth? So if I gave us a mixed number, how do we come up with an improper fraction? Or if I gave us an improper fraction, how do we get the mixed number? All right, so let's start with an improper fraction. So let's do, 22/5. So it's an improper fraction because the numerator is greater than the denominator. How do I rewrite that fraction? Well, I mean, I could start drawing out pizzas and chopping them into 5 pieces. And that wouldn't take us too long in this case because the numbers aren't huge. But if the numbers start getting bigger, that strategy is not optimal. So 22 divided by 5, well, you've got to kind of know your multiplication tables and division if you want to carry this out. But yeah, we're just going to do division. What is 22 divided by 5? So how many 5s go into 22? And we could write this out as long division. But
5, 10, 15, 20, 4.
4 5s. So yeah, we can count by 5s. We're pretty good at that. So yeah, if you had 4 5s, you'd have 20. So this would be 4. But then how many were left over? So we accounted for 20/5, but then there's still 2/5 left over. So this is 4 and 2/5. So or if you did the long division, you'd think of this as 4 remainder 2. So that's 4 and 2 parts out of 5, 4 and 2/5. So short answer is do long division and then put the remainder part over the divisor. All right, that's how we would convert from an improper fraction to a mixed number. Let's talk about the reverse conversion. All right, suppose we had, 3 and 4/7. We want to convert this to an improper fraction. And there are multiple ways of maybe organizing your work, but let's try this. This is really the same as 3 plus 4/7. But we know that if we want to add a fraction to something, we have to have a common denominator. So we're going to do our good old trick of multiplying by 1. We're always allowed to multiply by 1. So I'm going to do 3 times 7/7, because that's just a fancy way of writing the number 1. All right, and when you multiply something by a fraction, you can think of this 3 as 3 divided by 1, if that helps. But that's 21/7 plus 4/7. And yeah, 21 divided by 7 is 3. And now we can add the numerators and we just keep the denominator. We get 25/7. So we started with a mixed number. We've ended up with an improper fraction. And yeah, we can convert back and forth. And so this will be a skill that you're going to need. I know it's not the most exciting of math that you've seen, but don't skimp on this thing because it will help you in your future math classes.
And I have to say this one's especially useful with multiplying recipes, because a lot of recipes will have fractions with like a half a cup of this or a quarter cup of this. And if you are making, you want to make a triple batch of chocolate pumpkin chip cookies and you're going to freeze half of them, knowing how to manipulate fractions really helps a lot.
Indeed. All right, so that concludes our math lesson.
All right. Before we do what's in the bag, I want to answer a couple excellent questions that came in about viruses, just real fast. Excuse me. So one question was, how does hand sanitizer work? And are we killing good bacteria by using hand sanitizer? That's a great question. So let me draw a little bacteria here. So bacteria have a cell wall and a membrane. And then viruses have a membrane, and they've got these little proteins on the outside. And both of these, if you put them in 100% alcohol, either rubbing alcohol or isopropyl alcohol, that alcohol breaks apart the membrane, and then the virus and bacteria essentially just kind of dissolve. Soapy water can do a similar thing with harming the membrane, but most importantly, when you wash your hands with soapy water, that pulls, the viruses and the bacteria come away from your skin and they get washed off. So when you use hand sanitizer, are you destroying good bacteria? Yes. Hand sanitizer, alcohol, close to 50% alcohol is always going to be disruptive to any virus, any bacteria on your skin. But it's a good idea to get rid of that bad bacteria. And the good bacteria that you have on your skin, they're pretty resilient. And you touch your face and it's like, aha, you've been recultured with those good bacteria. They're going to be there no matter what. It's the bad ones that you want to get rid of. And then another quick question that we had about...
Wait, clarify. So is it better to wash your hands or use hand sanitizer?
It's better to wash your hands.
Okay.
So if you have to pick between washing your hands and hand sanitizer and you have access to soap, wash your hands with soap. Because that does the best job. If you lather for 20 seconds and then rinse, that does the best job of getting rid of any potentially dangerous viruses or bacteria. But if you don't have access to soap and water, and sometimes you don't, hand sanitizer is pretty effective too, and is a good substitute. And then another good question that we had, how does medicine for a virus or a bacteria work? This one's kind of a big question, but I'll just answer real quick. A medicine for a virus, you either have an antiviral that will slow down how it replicates, or you get a vaccine. And that's a way of telling your immune system, so here's a white blood cell, telling your immune system, haha, this is what you need to be on the lookout for, and then they can attack it. For a bacteria, usually what we use are antibiotics, and most antibiotics work by attacking the cell wall in the bacteria because our cells don't have cell walls. But the thing about antibiotics is that bacteria can evolve to be resistant to them. So you really want to be careful if you have antibiotics not to use it incorrectly. You don't want to just finish half your medication and then stop, because then you're encouraging those bacteria to become resistant. And you also want to be careful for antibiotic-resistant bacteria, because we're starting to get more of those now because we've been overusing antibiotics.
All right.
And now
it's time
for what's in the bag.
And no, I didn't get a brag. I didn't put this in, but I do have a what's in the bag challenge for Science Month.
I'm kind of excited because this is the very first time I'm being challenged to answer a riddle.
All right, so 4 fingers and a thumb.
It's a hand.
Oh, how do you know? No, it's not.
I'm sure it's not a hand.
It's not a hand. Okay. Yet flesh and blood I have none.
4 fingers and a hand.
No,
4 fingers,
and a thumb.
Yeah,
yet flesh and blood I have none.
A glove.
Oh man.
It's a glove.
I only come out in winter. Yes, it's a glove. It's a glove.
You can wear gloves when it's not winter.
No, not according to this riddle.
Not according to that riddle. Shout out to Megan and Rachel and Carrie, who also got the What's in the Bag challenge. Good job, you guys.
That was a good guess, too.
Ooh, a skeleton is a really good guess.
All right. So up next, it's time for our engineering challenge, which is something we have not actually tried, as usual.
I saw a cool picture of this online, and said, oh, we should do this for our engineering challenge. But then I haven't had a chance to practice it. And I told Math Dad, like, all right, heads up, this is what's coming. You should try and practice this. And he's looked up instructions on how to do it. I have not. So our challenge is, can you balance
want to
fork on a toothpick or a match?
So you get two forks, and yeah, they're not allowed to touch anything. They've got to be in the air, other than they can touch a toothpick. So.
Now, while Math Dad is setting this up, I want to say real quick about yeast, because yeast might be something that is starting to be in short supply. In my grocery store right now, if I go and try and buy yeast, there's not going to be any. And this yeast that we woke up right here, we can actually use this little experiment we did to grow our yeast and then dehydrate it. So I have my yeast that is in the flour, my yeast that is in the sugar water, and our balloons actually sprung links. I would recommend don't use water balloons because they did not work very well. But if I pour this out now onto a pan, and I would want to spread it thinner than what we're doing now after we do our show. I'm going to spread it between two pans so it's nice and thin. And then if I put it in a warm place, like an oven that I've preheated, and then I turn off the heat and I dehydrate it and then break it up into small pieces, I can actually use that just like I would use regular yeast. It's going to take a little bit longer to wake up, but because I gave it food and flour and water, I now have more yeast here than I had in the little packets, and I can dehydrate it again, and then I can use it to bake with. So that's a cool little hack you can use to get yourself more yeast.
All right, so I've stuck my two forks together here, and now I'm trying to wedge my little toothpick in there. And so what I'm trying to do is to get this so that the center of mass of these two forks is actually directly where the toothpick meets the jar here. But the jar is not important, it's just something to balance on. Having trouble actually wedging this in.
So I've seen before where people will put forks together like this and they'll stay. And maybe we should have tried this first, because my forks don't even go together. Like, I can't interlock them.
You just don't have enough faith.
Unless I do that. Ooh, I put them like sideways.
I don't know if that'll dangle in a way where the center of mass is away from the bodies. That's the challenge there.
Yeah.
And I did actually see a variation where people were using a spoon, and a fork, just wedging those together. I mean, we're using matches. Let's see, is this just too thin? Maybe that's part of my problem.
Here you go. Do you want a match?
Yeah, let's try a match. It's a
Matches
little bit
are a
bigger.
little thicker.
I might actually wedge. 4 times bigger than normal. I don't know. No. Come on.
So the challenge is to make a sculpture out of silverware and a match or a toothpick. Bonus points if you don't use tape, but I'm totally going to use tape right here to make my sculpture, because in just, the 5 minutes that we have left, I think that's the only thing that's possible. So here is my sculpture, duct taped to my jar. Ta-da! First.
Oh, so I'm not wedging in the right place. Oh, I broke a match. The match broke. What?
Do you know that one of our fans wrote a new song for you to sing?
Really?
Yes.
Does it go like this?
No.
I'm singing a song, I don't know the words.
So how can you know?
I don't know the words
How
to
can
this
you not
song.
know the words if you sing the
I'm
same words
singing
every
it
time?
loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song.
All right, now shout out to Madison. Sing these lyrics that make much more sense.
All right. I'm singing a song, I know the words. How else would I sing this song? I'm singing it loud and I'm singing it long, because I know the words to this song. This very annoying song.
Yes.
What? Annoying.
Well done.
I don't know what you're talking about. What? Okay, no. There's got to be a better way of doing this.
So we're supposed to go on now to our math mystery and the second art showcase, but I think Math Dad is taking it personal with his fork and his match, and he's like, I'm not leaving until they balance.
It looks so easy on YouTube. You know how that is. Yep.
So the video that you watched, the instructional video, they just put the forks together, they put a match in, and then they balanced it on a cup?
Yeah, it just balanced right on the end. I actually saw one version where they had this long toothpick balancing there, then they set the other end on fire so it burned back, and it was literally just balancing right on the edge then.
Oh, wow.
That was all that was left of the match or the toothpick. Well,
hopefully you've been inspired to go and do better experimenting than we just did. Although I will point out that my squeaker is totally functional with the duct tape.
Yeah.
This is what we call an engineered, yeah.
That's called cheating. That's what we call it. Cheating. All right. So for our math mystery, last time I left us with a challenge problem, and I'm racking my brains. It was a probability problem. That's what it was. Okay. So the question was, which is more likely? So there were two scenarios. Scenario A, we had roll 3 straight 10s when we're rolling 2 different dice, and the sum would be 10. Or scenario B, which was roll 4 straight 7s. And it wasn't clear which of those would be more likely, which of those outcomes. And in the first couple of days of this week, in our math lessons, we were actually learning about how to calculate such probabilities. So let's look at scenario A. So the probability of scenario A occurring would be equal to, so if I want 3 consecutive 10s, well, I just need to find the probability of getting 1 10 and then multiply by that probability a total of 3 times, and that will give us our answer. So when you had 2 dice, we said there were 36 equally likely possible pairs we could get. And which ones would give us a 10? Well, that would be a 4 and a 6, a 5 and a 5, and a 6 and a 4. So out of the 36 possible pairs, exactly 3 of them work out to be 10 as the sum. So in that case, the 3 out of 36 is the same as 1 out of 12. There's a 1 in 12 chance of getting 1 10 times 1 over 12 times 1 over 12. So it's 1 over 1,728.
All right, I think we should try it right now. I'm going to roll these dice. We'll see what we get.
All right, let's do this.
All right. Does that count as legit rolling if I
as long as yeah, you got a 1 and a 3.
1 and a 3. Oh, we didn't get a 5. Do it again.
You're going to do it 1,728 times.
No, I'm going to do it. Got a 7 this time.
All right.
That's our most common. Oh. Whoa. And that one's a 3. We got a 4. We got another 7, but no 5s.
Yeah, so 7s are more likely to show up, but getting 4 straight 7s, that's a little less clear.
We got 2 straight 7s.
All right. What about scenario B here? We've got to roll 4 straight 7s. So we're going to do the same thing. What's the probability of rolling a 7? We actually answered that one last time. It turns out there were 6 pairs that would give us 7. So we do 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1. So that was 6 out of 36 or 1 out of 6. 1 out of every 6 rolls will actually be a 7 on average. All right. But we wanted 4 of those. So I'm just going to multiply them out. So 1/6 times 1/6 times 1/6 times 1/6. So that's 1 over 1296. And that number is bigger than 1 over 1,728. So the answer is scenario B was the more likely of the 2 scenarios. You're more likely to get 4 consecutive 7s than you are to get 4 consecutive 3s.
3 straight 10s, you mean?
Yes, than 3 straight 10s. That's
yes.
what I meant. Numbers are hard.
We got 2 7s. Should we see how many more we can get?
You go ahead.
All right.
You just show me how this works.
7.
That's 3 consecutive 7s. That's pretty random.
Oh.
9. All right.
So we got 3 consecutive 7s. Go us.
All right. So that's probabilities, and yeah, probabilities relate to a lot of different things, including the Punnett Squares that we never had a chance to talk about.
Someone has been asking for the Desmos code for your cool math fraction practice one. We will update the description with several of the decimal code Desmos codes. But we might. Do we have it on the banner?
Most recent banner may have it. Yes. Yeah, go
so
ahead.
Yeah, we will update the Desmos code on the description later. But yeah, why don't you give them the next one, and I'll see if I can find the banner.
Okay. Well, and I actually built something just for today's challenge problem, somewhere where you can test this out. So here is the question for today. There are 10 balls, not 10 balls. There are 9 balls, rather. And all 9 of these balls look identical to each other. And in fact, they are identical, except one of those balls is slightly heavier than the other balls. And you have at your disposal one of those scales where you try to weigh things. And you can set the balls in the scale and you can weigh them, and you could try to figure out, right, which of these balls is going to be the heaviest.
Do you want me to share the Desmos?
Yes, go ahead.
So here is the screen. Oh, but it goes so big you can't see the actual code.
Well, just a second, I will get there. So it's 9B8F34. I'm going to write that out. But yeah, 9B8F34.
And again, we will update the description of the video with that as soon as we are done.
Okay, but I'm going to. All right. So just as a sample here. So that there are 9 balls sitting here, and those 9 balls can be dragged onto the scale here. And then once you've placed whatever balls you want to place on the scale, you can test. You hit the test button and it says they weigh the same. All right, so neither of those balls can be the heavy ball. So we could pick some others to weigh. Maybe I would.
Ooh, and that one's heavier. We found our heavier ball.
Yeah. Whoops, that wasn't supposed to register. We were. I'd forgotten about that mistake. At any rate, yeah, we need some strategy that would let us identify the heavy ball, and you only get 2 weighings. That's all you get to test.
So if you get lucky and just drag the heavy ball on, you'll know. But you don't want to rely on luck. You want to rely on your reasoning skills to figure it out.
Yeah. So that's my challenge for you guys. Can you figure out how to identify the heavy ball in only 2 weighings? So that's my challenge problem, our math mystery for today.
Awesome. I'm going to leave that Desmos code right here, and I'm going to answer. We had several people asking about the yogurt. So real quick before we finish, I'm going to just tell you how to make homemade yogurt and explain how it works from the lactobacillus' point of view, because this is really pretty cool. So first step is that you take milk and you heat it. And when you're heating the milk, there are 2 important things you're doing. And you heat it so that it's steaming and almost boiling. You're making sure that any other bacteria that happen to be in the milk get killed because it gets too hot. And you're also changing the way that the proteins are structured just a little bit so that then your yogurt is going to have a better texture. And then you let the milk cool down to about 110 degrees Fahrenheit. So that's like a hot tub temperature. If you can put your finger in the milk and it feels kind of nice and warm and pleasant, but a little bit hot like a hot tub, like, oh, this might be too hot for me to take a bath, that's a real good temperature. It can be anywhere between 110 degrees Fahrenheit and 100 degrees Fahrenheit, like your body temperature-ish, up a bit higher. And you incubate for about 8 hours. You can go a little bit longer. If you go longer, your yogurt will have a stronger flavor. You can go a little bit less. If you go less, your yogurt will be softer and a little bit more liquidy. and it won't have as strong of a plain yogurt flavor. It all depends on your personal taste. If you have it in a pot, you can wrap it in 3 or 4 towels to insulate it. Or if you have a crock pot, you can put water in there and put it on a low setting, or you can use your oven. Oh my goodness, Math Dad just got the engineering challenge and he's so proud of himself. I gotta show you really fast.
I know, because some little 6-year-old's going to show me up at home. So I had to make sure I could get this thing done. Can they see it?
Yes, they can see it.
Yes.
Yep.
Balanced on a match. Victory
Balanced on a
declared.
match. He is super proud of it. And I'll say it's totally okay if he gets shown up by our 6-year-olds who are watching.
Yeah.
Because we have awesome viewers. After you incubate for 8 hours, and when you get it to this nice cool temperature, that's when you add a spoonful of plain yogurt. So you have to have a spoonful of yogurt to make more yogurt, because you need that initial start of all those lactobacillus bacteria. But just using 1 spoonful, then you can make a whole quart of yogurt. After you incubate it, then you put it in the fridge to cool it down, and then it's ready to eat. So that's how you make yogurt. It is now 9 o'clock. We will end by showing you the engineering challenges that came in, and tomorrow's.
Yeah, so what are the prompts? Yeah.
Tomorrow's engineering challenge is to build your own silverware sculpture, and I'm sure you can do a way better job than we did. And tomorrow's drawing prompt is to draw something from the point of view of an ant. So look around your house, find something you want to draw, and then get down on the floor and imagine if you were an ant, what would it look like? Those are the drawing prompts for tomorrow.
That could be hard.
And then I gotta say real fast, I am so thankful for everyone who has joined us on Patreon the last few days. And if you're not aware of it, we have a cool little reward for the $20 patrons of some pins that we're making. And for April, it's There's No Planet B pin and some stickers. We're really excited about those. They're in production. And here's the first proof we got of May's pin, the little Science Mom Squad. So I wanted to share that. All right. Nice. Now it's time to end with our slideshow.
All right. Yeah. It's DNA molecules.
Yes. So we had some fantastic DNA structures with the pipe cleaner.
Yeah. They got theirs to twist nicely.
That is some nice twisting. I'm impressed.
Shape.
And some from our art drawing with the scientist yesterday. Great artwork there, and gummy worms.
I ate too much candy yesterday. I was kind of sick.
Some great work for Shab.
Ooh, an ant bee ladybug.
And more pipe cleaner. Good job, you guys. Nice paper structures here, and awesome drawing here. Great work, Boston.
Yeah.
And you know what? I love what they wrote here. If you don't have the resources, you can totally adapt. And they drew some great art. Some nice cardboard strand there. I love it.
Real good helix shape.
And some nice licorice and marshmallow.
Mark and Caroline, I like it.
And that's the end. I will be back in just about 15 minutes with Drawing with a Scientist, and there is a printout today. If you would like to extend your science learning and paint along or color along and draw the good, the bad, and the bubbly, we'll be talking all about these little viruses and microbes and bacteria, and I'll be back in about 15 minutes with that. Thanks again for watching, and we'll see you again tomorrow.
Bye.